Hello, hello, everybody. We're going to talk about section 3.4 today. So this is about the graphs of polynomial functions. So for this first example that they give us, they say find the x-intercepts of x to the sixth minus 3x to the fourth plus 2x squared. So what that means, the x-intercepts, try to do this more straight, there we go. So the x-intercepts are where f of x, also known as y, that's where y equals 0, or you could alternatively think of that as where f of x equals 0. That's what they mean when they say find the x-intercepts. So basically what they want us to do is they want us to do 0 equals x to the sixth minus 3x to the fourth plus 2x squared. Now you can solve this for where it equals 0 by factoring it. So the first thing to notice, each of these has at least x to the second power for each of the terms. So if you were to factor out x squared from all three terms, that would leave you with x to the fourth. The middle part would be minus 3x squared. And if you divide out x squared from this, all that would be left would be plus 2. Then what you would do is you would factor this. You kind of set this up the way maybe you normally set up factoring here. You get yourself a couple of parentheses. This might be a little different than what you're accustomed to, but the big idea here is if you've got x to the fourth right here, where that would come from if it was factored is you would have an x squared here and you'd have an x squared right there. So that if you then used FOIL to multiply these things out with the parentheses, the x squared and the x squared together would give you x to the fourth. Back in the back, you've got the number 2, and there's only one way to multiply and get 2, which would be 2 times 1. Since this is positive, you either have 2 positives or 2 negatives. Since the middle is negative, that basically means we're going to need -2 minus 1, because fun fact, -2 minus 1 will give you a -3. That would be in the middle. So then we would end up with this equation right here. And then what we can do is we can take each individual factor, and this is why we like it when it's equal to 0, because we can take each individual factor and solve where they equal 0. So you solve where x squared is 0, where x squared minus 2 equals 0, and where x squared minus 1 equals 0. This first one, you can square root that, and lo and behold, that just means that x is equal to 0. Here you would want to add 2, and if you do that, you get x squared equals 2. And then if you take the square root of both sides, that will tell you that the next set of solutions would be positive or negative square root of 2. And then lastly over here, if you add 1, you will get x squared equals to 1. You're going to need to square root each of those. Square root of 1 is 1. So that tells you that x should equal plus or minus 1. And just remember, when you solve and use a square root, there's both a positive answer and a negative answer at the same time. Now, these are the solutions. And if we were to write these out as intercepts, because the x-intercept is a point, so you would have the point 0, 0. You would have root 2 comma 0. You would have negative root 2 comma 0. since these are X intercepts, all of the answers I have are X values of points. There would also be an intercept at 1, 0, and there would be an intercept at -1, 0. So all 5 of those would be X intercepts of that graph. Now, before we move on to the next problem, I do want to take a moment and look at the graphing calculator here for a second. So go to the graphing calculator. What we are going to do is make a graph of the polynomial that I just solved for. So let's see, what was it? It was X, and then raise it to the 6th power. We're done with the exponents, so then we should arrow over here. Then let's see, it was -3, and then we're going to do X, raise it to the power of 4. So your caret key right here. This one right there, that's your thing to raise powers. And then finally, what was it? It was +2x, and then +2x squared. So if we graph this, and I want to change my, let's go to come on, go to zoom and pick zoom standard. There we go. Okay. So there's what the graph looks like. And actually, I'll tell you what, let's go to window and we can zoom in a little bit. So maybe instead of being quite so wide, let's maybe go to like maybe -2 and +2 for the X values. And then if we graph that, that's going to be a little bit zoomed in here. So we don't have quite as much extra space on the sides. And then let's also go to, let's go to window, or no, let's see, window, here we go. Let's make the Y values a little narrower too. So let's maybe go, I don't know, let's say negative, let's just do the same thing, -2 to +2. So we'll change those to -2 and +2 so it doesn't go up quite so high. And so now you got this graph right here. And so if we hit the trace key right there in the middle, you will see the point at 0, 0 that we found just by solving it analytically without any picture. Over here, you will notice is +1. And over on the other side is -1. And I think we've used this before, but if you go to second trace, if you do second and then the trace key, which is right there, that'll take you to the calc menu. And what you can do is you can use the thing that says 0, and it'll find the 0 value for you on the graph, which is what we're trying to do. So like if we go over this way, they say give them a left bound. So the left bound, keep going over here, go to the left of this point right here. So we can press enter, there's your left bound. Arrow back over this way and go to the right of the point and press enter again. That's the right bound. Then they say, give me a guess. So you kind of get as close as you can. And lo and behold, there's the -1, which is one of the solutions we found earlier just by solving it analytically. And then something else you can do is you can do that all over again. You can also find the other value, which was, you might remember, it was the square root of 2. So you go to the left, go back over to the right of the point, and then go back to the middle, right about there. So that gives you -1.414, which is the decimal equivalent of the negative square root of 2. And so The moral of this story, part of why I'm showing you this, is that especially if you're, I don't know, a tad rusty with your factoring, or if you frankly just don't like it all that much, which I can't blame you. The thing to be aware of, and one of the big takeaways from this whole unit, is that when you're solving an equation, when you're solving for where it equals 0, graphically speaking, what that means is that you're finding the x-intercept of the graph. And in algebra classes from days gone by, like all the time you spent learning how to factor, a lot of what that does is it's graphically what you're doing is you're finding the intersection points of a parabola with the x-axis. That's graphically what that means. And there are reasons why those are significant, like in more advanced math, for why we care about those points so much. But what I'm showing you is a way to do it graphically so that you maybe don't necessarily have to be a master at factoring, because there are other ways to find and track down the answers you're looking for. So that's how you can use the graphing calculator to find the x-intercepts that you are after. Let's look at the next example. So here's another one where they say find the x-intercepts of this one. So here, this is going to basically review another factoring technique that presumably you've seen before. And again, you can always check these by doing a graph. I'm not going to do that for every single one, but just be aware that that is an option. So this technique is factoring by grouping, and we'll talk about what that means here. So it's finding the x-intercepts, which, as we mentioned, that just means set f of x equal to 0, and your goal is to solve x to the third minus 5x squared minus x and then plus 5. So when I say grouping, basically what I mean is we're going to take these terms 2 at a time and look for a common factor that just 2 of them have. Now, if you look at this first one, what you might notice, what they have in common, this has a maximum of x squared. There's at least 2 x's in this part. And then the front part, x to the third, there are at least 2 x's. There's at least x squared in this one. So you could factor out a common factor of x squared just from these 2 by themselves. If you take x to the third and divide x squared, what will be left is x. If you take negative 5x squared and divide x squared, all that's left would be minus 5. Let's see. I also wrote the problem down wrong. This 5 back here magically changed into a 1. Let's change it back to a 5, shall we? I'm not sure what on earth happened just then when I was writing it down, but anyway. All right, here's what I want to point out to you. This factor right here should always match the factor in parentheses back in the back, which is a useful fact to have at your disposal. Because once you know this is x minus 5, you know immediately the one back here has to be x minus 5. No ands, ifs, or buts. These must match. And I personally kind of like to work backwards when I solve these kinds of problems, because usually it's easier to work backwards. The question is, if this is x, what would I have to multiply in front here? What would have to go up here that when I distribute it would turn an x into a negative x? And the answer would be the number -1. And then it's good to check with the other value too. If I were to take -1, distribute it back here to the -5, -1 times -5 is +5, which is good. That checks out. So then what you're going to do is you're then going to regroup everything. And the way you regroup is you essentially do this. The things that are in front, what do we have? We have x squared and minus 1. So those are going to go together themselves in their very own set of parentheses all to themselves. And then you just bring down a single copy. You don't need to write it twice, but you just need a single copy of the factor x minus 5. And all of this stuff equals 0. You only need a single version of x minus 5 because, again, this is factoring. Big picture, what you're trying to do is get something that's like teed up so that you would like FOIL it if you took your answer and multiplied it back out. A way to check yourself is you can take this thing, multiply it by this thing using FOIL, and if all goes well, the answer you get from foiling it will match what you started with. That's just a way to check your work, but that's not actually something you like need to do to solve the problem. I've taught these concepts and had students where like they would factor something and then multiply it back out, and then they like went in a complete circle and their answer was like the problem you started with. And usually I wouldn't give them a whole lot of grief because maybe like the middle was correct, but what I would often stress to students is it's like that's just checking your work. Foiling and getting back to exactly where you started is not the goal of the problem because you've essentially gone nowhere. Like you started and ended at the same place. But anyway, what I'm trying to get across is the end result should look like something where you would FOIL it, where you've got two chunks of stuff with parentheses and you multiply them first, outside, inside, last. Like we did before, now that it's factored, that's usually the hard part. Now that it's factored, we're going to take each factor by itself and solve where each of those equals 0. So for this first one, since you are subtracting 1, the first thing you would want to do is add 1, and that gives you x squared equals 1. Over here, you would add 5. That will give you x is equal to 5. That one is finished. We're not quite finished with the other one because we do need to square root this. The square root of 1 is the number 1. Just remember that when you do the square root, you have both a positive and negative root because 1 squared is 1 and negative 1 squared is also 1. So there are 2 answers. So when all is said and done, the x-intercepts, what we're wanting are points. And x-intercept is a point. So what you would say, you would write these out separately. You'd have 1, 0. You'd have negative 1, 0. And then you would have 5, 0. And those would be the 3 x-intercepts of that equation, of that graph. And again, I'm not going to rehash all of the steps like I did with the previous problem, but just bear in mind another way to go about solving this and finding the x-intercepts is you can draw the graph, use the 0 function that the graphing calculator has, and you can find each of those 3 numbers individually, and that will tell you the x-intercepts of that graph. Okay, so I don't know why I clicked on that thing. Let's go back here. Okay, so let's see what else we have. Find the y and x-intercepts of the polynomial in factored form. All right, so like before, the x-intercepts, just to reiterate, the x-intercept is where y equals 0. And so we've been doing this, and this problem is actually kind of nice because since they've already factored it for us, we actually have less work we have to do. So that's kind of convenient. You've got x minus 2 squared, and then that equals 2x plus 3. So it's already factored. So we can just say, okay, here's x minus 2 squared equals 0. The way you would get rid of something squared would be to square root it. Fun fact, the square root of 0 is 0. And 0 is the only number where when you square root it, it only produces one value because 0 does not have a sign. The plus and minus 0 means nothing because 0 has no sign at all. There's no such thing as -0. You can solve this by just doing x plus 2 right here. That will give you just x is equal to 2. So one of the x-intercepts will be the point 2, 0. Meanwhile, this other thing in parentheses will give you yet another x-intercept. You do 2x plus 3. Let's make sure I write it down correctly. Unlike earlier, let's see here. So you're adding 3, which means you would subtract 3. There we go. And then you are multiplying by 2, which means you'd want to divide by 2. And that's going to give you x is equal to -3 halves. And then lo and behold, you have the point -3 halves, 0. Those right there are the x-intercepts. And part of the way you can tell they are x-intercepts is that if you solve for x, you have found the value of an x-intercept. And the other variable, y, would be a 0. Now, similarly, you notice they also ask us to find the y-intercept. And the thing to know about the y-intercept is that in the similar fashion, the name of the intercept tells you the other variable is 0. So that just means x equals 0. So then what this means is that we are going to take g of 0, and that means 0 minus 2 parentheses squared, and then multiply that by 2 times 0 plus 3. So what we're going to do is replace the x in the function with 0, work it out, and see what we get. If we do that, we'll call this y just for the time being. 0 minus 2 is -2 squared. 2 times 0 is just 0 plus 3. -2 squared, that's -2 times -2, which is a +4. If you're doing this in the calculator, make sure that you include the parentheses. If you leave off the parentheses, the calculator will lead you astray. That's going to be 4 times 3, meaning that y is going to equal 12. So then this is the y-intercept, which means we will have the point 0, 12 as the y-intercept of the graph. And I do want to take a moment and look at this one just really quickly. So let's go back to the calculator here. So we're going to go to the y equals menu yet again, clear out the stuff that's there. Type in the function exactly the way it was written. So we're going to have parentheses x minus 2, close your parentheses and square it. And then we're going to multiply that by 3x plus 2 in the other parentheses, and there you go. And then if we go over here to the graph button, and we don't see a whole lot because our window is still awfully small from before. Let's go to our window here. Now, I already happen to know from what I did earlier that the y value goes all the way up to 12. So I'm going to do my y max. Let's maybe jump it all the way up to 15, maybe. Do a 15 for the highest y value. And then maybe, I don't know, maybe we'll go to like -4 and +4. I don't think the x values were that big, if I remember. What were they? 2 and -3 halves. Yeah, the x values weren't like super huge. So anyway, we can kind of tinker with our graph here, our window here. So you get a graph that looks kind of like this. If you hit the, where is it? The trace key, which is right there, it'll actually put you, let's see, did I goof something up or did I type this in wrong? It's 2x. Okay. I typed it in wrong is the problem. It should be 2x plus 3. Let's try that again. So we're going to graph this. Okay, that looks a little better. And then we hit trace. There we go. So that actually matches the result I got from doing it analytically with no graph whatsoever. there you will find when you hit trace, it will start you automatically on the y-intercept, which lo and behold, is 12. Imagine that. So you have the point 0, 12. One thing you can do too, by the way, if you like already know what the number is supposed to be, if you go second calc, you can calculate a value. And let's see, what did we solve? So if we look at the picture, it looks like it hits at 2. And plus from the work we did earlier, we found that the x-intercept was 2 anyway. So you can also just calculate value and just put in an x value and see what it gives you. And lo and behold, that's the 0.2, 0. And so basically we've just checked our work and confirmed that, yes, I have the picture right in front of me. And lo and behold, the x-intercept is indeed 2, 0. And you could even do that with negative 1.5, which is, or negative 3 divided by 2, if you will, which would be how you would do 3 halves, negative 3 divided by 2. And lo and behold, negative 1.5, there it is. There's the other x-intercept. So yet another strategy or technique at your disposal for how to use the graphing calculator to double check your work. And I mean, honestly, you can go straight to the graph and just find them that way. You don't necessarily even have to do them analytically, but I'm showing you anyway, because there are situations where the graph has its shortcomings and we will need to solve them analytically. But you can always check your work, or some of the easier ones, just do them completely with a graph, which with the technology, I think a lot of people find easier. All right, finding the x-intercepts of a polynomial function using a graph. So here's one where they straight up tell us, hey, bro, you should make a graph. And I'll be like, right on, bro, I can totally do that. So we're going to go, what is this? Y equals x to the third plus 4x squared plus x minus 6. Okay. Okay, let's see. So here's what I'm actually going to do. I'm also going to show you there's a pretty snazzy online graphing calculator that is out there too. It's a website called Desmos. And if you go to desmos.com and push the graphing calculator button, it'll take you to a free web-based graphing calculator, because awesomeness. These are the miracles of the times in which we live. It is the internet has wrought more than just people making obnoxious statements in comment sections as though anyone really cares or should care. Anyway, we're x to the third plus 4x squared, x to the third plus 4x squared. And if you do shift 6, that's the caret key on a keyboard. It's the exact same thing you do for exponents, plus x minus 6. So plus x minus 6. So that's how you can like do. If you have this little keyboard symbol, if you do this, you can do powers this way. So you can do like this, and then it'll like take you up to do an exponent, but we're not actually gonna do that. So here you go. There's a picture of the graph, and we want what are we trying to find? We want the x-intercepts, okay? You got it, bro. Click on this point, click on that point, click on that point over there. How awesome is that? And what I'm going to do is I'm going to break out the snipping tool. And we'll do a screen capture of this very lovely picture here. Whoop. There you go. And let's copy this, and then we'll just drop it in the PowerPoint over here. Drop it like it's hot. There you go. So there's a graph. And again, you can also use the TI-84 with this stuff, but there you go. So you got negative 3, 0. You've got negative 2, 0. And you've got 1, 0. All right, there you go. Wasn't that easy? So there you have it. Those are the x-intercepts of that polynomial. And you can get a graph in front of you, and lo and behold, there they are. How about that? Okay, let us see what else we have, shall we? They say find the y and x intercepts of this function. So x to the fourth minus 19x squared plus 30x. All right, let's do a graph of this one here too. X to the fourth. So let's delete all this stuff. We got x to the fourth plus, then what do we have? Or it's minus 19x squared. Okay, so back up, minus 19x squared. That's one wacky looking graph there. And then plus 30x. All right, you got it. Plus 30x. All right, how about that? That is, if you want to zoom out and zoom in, you got these plus and minus things here. So you can like zoom out a little bit. If you also click and drag, you can like kind of slide it around and stuff. If you want to adjust the window, because like we got a lot of dead space here, like there's not much past -5 and +5. So maybe what we can do is if we click on this little wrench and say, all right, let's have x only go as far as like, I don't know. Let's maybe go to -6. Then we'll go to like, I don't know, +6 maybe. That's okay. This is just kind of an OCD thing, but I kind of don't like the end of the graph being cut off like this. So let's see. Let's do this as like a nice round. Let's just do 14. I don't like weird decimals. Let's see. Down there somewhere is the bottom of this graph. Let's try -20. That is not low enough. Let's try -50. That's still not low enough. Let's try -100. Oh my gosh, that is way down there. 250. Hey, there we go. Looks like 200 will be good enough. Okay, so -200. Okay, there you have it. That graph goes down pretty low there. But anyway, here we go. You can just hover over them and you find the X intercepts right there. So there you go. We've got this very nice, graph here. Let's see. Let's do a screen capture of this too, shall we? Whoop. Okay, so something kind of like that. Not quite catching all the top and bottom, but it's okay. So you can do that, and you can do whoop. That's a really big graph. So, no, I'm not interested in your design ideas, Microsoft. Go away, please. Let's see. So here we go. There's the graph. That's what it looks like. So all right. Find my little pen thingy. Okay, so the X intercepts. There are 4 of them, it looks like. We've got -5, 0. There's 0, 0. There is 2, 0, and there is 3, 0. So there you go. Those are the X intercepts. Then fun fact, the point 0, 0, guess what? That is both an X intercept and a Y intercept at the same time, because that is the point that happens to be located on both the x-axis and the y-axis simultaneously. Who knew? Okay, so there you go. You've got yourself a very lovely graph, and you've got intersection points on the x-axis, and then you've also got an intersection point on the y-axis. So there you go. Okay. What else do we have? So then here they say, notice the end behavior of the function at each of the X intercepts is different. Okay, so here's kind of the next thing, the next big idea that we have going on here. So this is the -3, and fun fact, that's going to correspond, these are called factors. Each thing in parentheses is a factor. So the factors, we have x plus, let's actually write the x down. So the factors, you have x plus 3, you have x minus 2. That's the next thing in parentheses. We're going to ignore the power there for the moment. And then we've got x plus 1. Okay, so each of these is going to correspond with an x-intercept, a point on the x-axis. And part of the goal of this section and this whole chapter in general is we're trying to make connections between what the formula does and then how that affects what the graph does. Try to get that link in our minds between this is what the formula looks like, and then the formula does this. It will have this sort of an impact on the picture that it produces. Now I've kind of ignored the powers for right now. Now the power of this one, the x plus 1, that's a power of 3. And the term for that, that's called a multiplicity. Multiplicity 3. And all that refers to is just the power that's attached to that chunk of parentheses. So when it says multiplicity, that's basically another way of saying it's got the power of 3. I got the power. Sorry, I'm not sure where that came from. Anyway, let's see. Next, here's the x minus 2. The power there is 2. So that again is a multiplicity of 2. That's all that means. It's just the multiplicity refers to the power attached to that chunk of parentheses. Now this, you notice the x plus 3 doesn't have a power. If you wanted to, you could say that it has a power of 1, because what this means is it's like x plus 3. X minus 2 squared means x minus 2 shows up twice. X plus 3 to the third means that if you wrote them individually, it's x plus 1 times x plus 1 times x plus 1. But since ain't nobody got time for that, writing that much, they just write it one time and then they put a little 3 up there to just tell everybody, hey, just so you know, this x plus 1, there's actually like 3 of them. I'm just going to write it once and put a 3 up top just to save time and space. But just so you know, that's really like legit what this means. Now this, since the x plus 3 only shows up one time, the power would be 1. And fun fact, raising something to a power of 1 doesn't actually do anything. It's just the exact same thing. But strictly speaking, for those who are keeping track, this would have a multiplicity of 1 for those playing the home game. So there you go. That's a multiplicity of 1. Now, okay, well, so what? Big deal. We got multiplicities. Okay, well, what's the deal? What's the big deal? Here is the takeaway. Here's the thing to know. Get ready for this. Even multiplicities, this is not the technical term, but they bounce off the x-axis. There are 2 F's and off. So if you think of this like it was a ball, like you throw a ball and it goes boom, and it bounces off the x-axis. You toss it and it goes boom, and then it bounces back up and it goes back where it came from. Again, bounce is not the technical term, but I think it's kind of a nice visual. Odd multiplicities. Odd multiplicities just cross the x-axis. I've also seen books that use the word cut. So either they cross or they cut across, I don't know. They cross the x-axis. And basically what that means, so the one with the even multiplicity is this guy, which corresponds to that one right there. That's giving you the 0 at +2. And then notice that has the even multiplicity, which means that the graph goes down, it bounces off the x-axis and goes back where it came from. Here you have -3, which corresponds to the x plus 3. And so that is cutting across the x-axis right there. This one is -1, so it's crossing at -1. So this one, let's see. So this is basically giving you 2, 0. The -2 gives you 2, 0. +3 gives you a -3, 0. +1 gives you -1, 0. You'll notice it's just like switching the signs around is all it is. If the factor is x plus 3, it's -3. If the factor is x minus 2, it's +2. You're just switching the signs around is all it does. And so at -3, it crosses because its multiplicity is an odd number. At -1, it also crosses the x-axis because the multiplicity is an odd number. So that's sort of the big takeaway of this whole thing. Even multiplicities will bounce and odd multiplicities will cross the x-axis. Here, this is just kind of more of that same theme here. So if the P is 1, it's very line-like, which we would, if we go back to this one here, the one at -3, where it's a multiplicity 1, this is very line-like because it's a lot like y equals x plus 3. It's a lot like an equation of a line. A cubic graph is like an S curve. And so what this is just showing you, a multiplicity of 3 is going to give you an S curve, which looks a lot like the x cubed graph. This is like y equals x cubed. This one is like y equals x, which is a line. And then this is kind of like this one here is kind of like a parabola. This is like, this one is like y equals x squared, and it's sort of vaguely parabola shaped. So you can even go a little bit farther than what we were just talking about, because the size of the power also tells you, like, does it cross kind of like a line? Is it more of an S curve? Is it more of a U curve? And it kind of behaves like either a line, a parabola, or a cubic graph where it's like an S curve. All right, so use the graph of a function of degree 6. I don't know if we've defined what degree means yet or not. I think we have. I'm not remembering, but it's easy enough. I'll just tell you again, even if I've told you before. It's degree 6, and identify the zeros of the function and their possible multiplicities. Okay, well, let's find these points here, shall we? So we've got this point right here. That's -3. So we have a point -3, 0. That's going to come from that one right there. We've got another point right here. This is going to be -1, 0. We've got kind of a gap, and then you've got this point all the way over here, which is 4, 0. Now, the 3, 0 part, that's bouncing off like so. If you focus on just this part here, what you will notice is that that's sort of like a U shape. If you zero in right here, at this point, the -1, that's kind of a lot like a line. And then if you zero in on this one right here, this is kind of an S curve. So then, like we were talking about on the previous slide, this is going to be a power of 2, because this is sort of parabola-esque. It's going to be like an x squared graph. This is a line, which would be like a power of 1. This is kind of an S curve, which would be a power of 3. Now, we need to get factors. These are called the zeros or the X intercepts. Another term is the zeros, the X intercepts. What we want are the factors. So we need to write them as things in parentheses that would be the factors of the polynomial if you factored it. So the factors, -3, that would correspond to X plus 3. -1 would correspond to X plus 1. And then 4 would correspond to X minus 4. We said that the one with the 3, that comes from a power of 2. The 1 comes from a power of 1. And the 4 comes from a power of 3. Usually we don't bother to write a power of 1. So if I were to write a function for this, I would say f of x equals x plus 3 squared times x plus 1 times x minus 4 to the third. And one thing I want to come back to as well, because I have not yet mentioned it, degree 6. The degree is going to be the sum of all multiplicities. That is what the degree will be. Multiplicities is just way too long of a word. Oh my gosh. Anyway, it's the sum of all multiplicities. So what do I mean by that? Well, here's 2, 1, and 3. And lo and behold, 2 plus 1 plus 3 equals 6. And boom, there you go. That is the degree. The degree is 6. You add up all the multiplicities, you get 6. There you go. That would be a polynomial that would roughly match the graph that they have given us. And so again, sort of the big idea for this section and for this chapter as a whole is we're trying to get across a sense of the connections between what does the formula do and then what impact does that have on the picture. And here we're kind of going in reverse. We start with a picture and try to come up with a formula that would correspond with that picture. All right, something else in this section, we've got something known as the intermediate value theorem. Now, what does the intermediate value theorem say? Well, it says let f be a polynomial function. The intermediate value theorem states that if f of a and f of b have opposite signs, then there exists at least one value c between a and b for which f of c equals 0. So what does that basically mean? If you know that one side's negative and one side's positive, that means that at some point in between, you had to have crossed 0. You had to have hit the point where you cross from negative territory to positive territory. And this is part of the significance of finding zeros on these kinds of graphs in the first place, because something that is often the case in, say, physics or chemistry or even in like business classes, because there's a business calculus is a thing where you do highfalutin math to try to maximize profit and stuff. But the general point is knowing where you go from negative territory to positive territory can be a big deal, and it's really important. And so all the intermediate value theorem says is if one value gives you a negative and another value gives you a positive, somewhere in the middle is a 0. You don't necessarily know where it will be, but you know that it exists. And often in mathematics, that's a useful first step. It's good to know something exists before you do a lot of effort and energy trying to then find it. Because fun fact, if it doesn't exist, it is not worth your time trying to find it. All right. Anyway, show that the function, so here's the function, x cubed minus 5x squared plus 3x plus 6. show that it has at least two real zeros between x equals 1 and x equals 4. So what does that mean? Well, here's what we're going to do. Let us find f of 1, f of 2, f of 3, and f of 4. So we're basically just going to start at 1, go to 4, and we're just going to plug them in and work out this function for each of these values. So 1 to the third minus 5 times 1 squared plus 3 times 1 plus 6. That's going to be 1 minus 5. Let's just do this in a calculator. I don't need to impress. I don't need to impress you. Let's see. 1 cubed minus 5 times 1. Let's see. Times 1 squared. And then what is this? Plus 3 times 1 plus 6. So you work all that out and you'll get the number 5. Okay, and then you do that all over again, this time with 2. 2 to the third minus 5 times 2 squared plus 3 times 2 plus 6. And let's see what that is, shall we? Should do this all over again, make all those a 2. Oh, what is that? That's 0? Okay. That's 8 minus 20, which is negative 12. Okay, so that's 0. Let's see, what is 3? So that's 3 to the third minus 5 times 3 squared plus, then what? 3 times 3 plus 6. Okay, let's see what that is, shall we? So that's 3. That gives me negative 3. And then once more with feeling, here's 4 to the third minus 5 times 4 squared plus 3 times 4 plus 6. Okay, so what is this? So that's a 4. That's a 4. That's a 4. You work all that out and you get 2. Okay, so what does this mean? Well, from here to here, that's positive to negative. And then from here to here, that's negative to positive. So there are 2 changes, which means that there are at least 2 zeros. And we actually inadvertently found one of them, because we actually happen to know that at 2, you do in fact get 0, but then somewhere between 3 and 4, there's going to be a 0 somewhere between f of 3 and f of 4. We don't necessarily know where exactly it'll be, but we do know it exists. And all we really care about is just showing that it exists. Okay. So that's basically what the intermediate value function says. You put in numbers to the function, and if you pick like numbers that are like next to each other in a range, then you're basically saying, okay, if one input spits out a positive number and another input right next to it spits out a negative number, then somewhere in between them is going to be a 0 value. Write a formula for the function shown in figure 19. So this is kind of going back to what we were doing earlier. This is sort of similar. to what we have been talking about. So you have a -3, a +2, and a +5. So let's see. So you have -3, and it looks sort, if you sort of zoom in on this section of it, what you will notice is that that looks very sort of line-like. So that suggests it's going to be a multiplicity of 1. The next value is at 2. And if you kind of zero in on this part of the graph, what you will notice is that that looks sort of parabola-esque, meaning you have a multiplicity or a power of 2. That's like an x squared graph. And then if we kind of zoom in on this one right here, what you will see at 5, that also looks sort of line-esque right there. There's 5, and that looks kind of sort of like a line, which suggests that this has a multiplicity of 1 as well. So then all of these numbers are going to do like a switcheroo. If we're going to write a f of x function here, we're going to say, all right, this will be x plus 3. Multiplicity 1, we don't necessarily need to write down. If it's 2, we're going to write that as x minus 2 and then square that because the multiplicity. And then this right here is a 5. So we're going to have x minus 5 right here. And there you go. You have yourself a function in factored form that will resemble the graph that we have. Okay. Let's see here. There's one other thing that we should look at because we're not quite done here. Okay. Oftentimes there is usually some sort of multiplier, which they usually call A right here. So the question is, what do you do to find a value of A for like your leading coefficient? Well, here's the thing to notice. You've also got this point right here, which is at 0, -2. So what that means is that if you put in 0 for the x, you should get -2. So what that means is you should get a y value of -2. You'll have some a that I don't know. And this will be 0 plus 3 times 0 minus 2 squared, and then times 0 minus 5. Now we can work out a lot of these numbers here because this is going to be 3. This is going to be -2 squared, and that'll be -5. Let's see here. So -2 should equal, let's see here. That'll be 4. 4 times -5 is -20. -20 times 3 is -60. So you have -60a. And our goal is to solve for a. If we divide by -60, then we will get an a value of 1/30. So then if we are going to write a polynomial for this, what we're then going to do is say, okay, f of x will equal 1/30, x plus 3. I'm desperately short on room here. Hold on. Let's try this again. So the answer, after we find that, the answer is going to be f of x equals 1/30, x plus 3, x minus 2 squared, and then x minus 5. And then that will give you a function that will correspond to this graph right there. Okay, We've got one left here. What is this? This is just mainly to acquaint you with some terminology. So like this point would be considered the local maximum because in the sort of localized region of the points around it, it's the high point of this particular bump in this neighborhood. It's not the global maximum, which is like the absolute highest point on the entire graph, but it is a maximum in this sort of local area. And then there's this point down here, which in this local area, it is the lowest point in this sort of neighborhood, although there are points like down here and here, for instance, that are lower, but within that localized area, it is the low point. And this is also a graph that does not have a global minimum because since it's going down forever, there is no overall minimum that it reaches because it just keeps going down and down farther and farther and farther. So that's mainly just to help you be familiar with some terminology. Okay, that is the end of that section.